Great. Thank you, everyone. It's really lovely to be here and to be presenting this information to you. It's great to be part of this project, and thank you, Mel, for such a wonderful introduction to isotopic traces in mosses. So here I'm going to present isotopic traces for measuring the hydrological cycle, but I'm going to give a very generalized view of some of the traces that we use. I'm new to the Antarctic and the subantarctic, so I'm going to talk about some of the traces we have and where we've applied them in other environmental systems, and how we're aiming to apply them in the subantarctic and more broadly in the Antarctic. So we're looking to get suggestions and collaborations on where we can apply these types of traces for this project. So just to begin with, ANSTO has 3 researchers that are contributing to the SAEF project. And that comes with Kwan. He's doing the radiocarbon dating. Some of that work that, that Mel was just talking about is done by Kwan and his laboratory. And also we've got Christina Saunders, who has a vast history of working in the subantarctic and Antarctica, and she's going to be looking at the paleoclimate records. And I'm going to be contributing through isotope tracing and hydrogeochemistry. So our team will contribute to themes 1 and 2 of these particular, of this project. So for those of you who haven't been to ANSTO or don't know about ANSTO, we're actually an Australian publicly funded research facility. We also have our own internal research organisations, projects, but we also run some of the largest science infrastructure in Australia, and that includes the synchrotron down in Melbourne, the Centre for Accelerator Science, which is up here at Lucas Heights, and we also have Australia's only research reactor here at Lucas Heights. So Mel just talked a lot about the carbon isotopes. So in the environmental research theme here at ANSTO, we use a lot of different isotopes to trace environmental processes. It's our bread and butter type activities. I mostly use carbon, hydrogen, oxygen and nitrogen, but I use the stable and also the naturally radioactive forms of these isotopes. But in a lot of my work, in my postdoc work, I was looking at developing up some of the trace element isotopes that can go into complementing a lot of our standard isotopic traces for understanding more fine scale processing in the environment. We also access things like some of the noble gases. We look at the isotopes of those particular elements as well. They can be quite useful for looking at ice cores. So I'm just going to give a little bit of a broad brush summary of some of the research outputs that we undertake here at ANSTO. And we've been doing work down in Antarctica previously. We've also done work in the Arctic as well. And we've used isotopes to trace various processes or understand various landscape evolution processes. So for an example, we've looked at radiocarbon in methane of gas bubbles contained within ice cores. And we also use beryllium to understand landscape evolution down in Antarctica also. So we not only look at ice cores and those types of climate archives, we also look at things like speleothems for paleoclimate information. We look at we have a well-renowned team that work on looking at the calcium carbonate laminations in speleothems and recording and measuring the isotopic value contained within those particular archives. And things like oxygen 18 can be used to understand past rainfall conditions within a region, and then that information can be used to understand past environments. We not only look at paleo systems, we also look at, we've been contributing to archiving modern environmental processes. And one of the ways that we're doing this is we're collecting rainfall data from across Australia. We've been doing this for since 2006, where we've been collecting monthly rainfall samples. And this information is invaluable because it shows the types of atmospheric processes and rainfall events that are contributing to the recharge and the replenishment of our river systems and our groundwater systems. So to get back to where I come from as a researcher, I'm a groundwater hydrologist, and I use isotopes to trace the water molecules as they enter into an underground system. So we look at how rainfall recharges into a system and how it then infiltrates into the ground. And we use these isotopes such as radiocarbon and tritium to understand the age of the system and understand the sustainability of a particular system. We also use these isotopes to understand what type of rainfall events are recharging our systems and our rivers and lakes. And we also use them to trace the source of salinity or the source of contaminants, whether it be natural or anthropogenic induced. So that's where I come from, that's my background. And I also use a lot of these trace element isotopes, as I mentioned previously, to understand some of these finer scale processes. In particular, I use things like lithium and boron and silica to understand these particular isotopes are useful in the marine setting and also the terrestrial setting. So I'm really quite excited to be able to be using some of these tools down in, particularly for this project. So let's just bring it back to where we're studying. That's all quite a large overview of what we do here at ANSTO, but Karina Saunders has been working on Macquarie Island for the past 15 years and has been collecting paleo data from the lake systems that are contained on Macquarie Island. And she's also been doing some lake water sampling as well. And we wanted to do a greater survey of Macquarie Island and really understand the contributions from the bedrock sources together from marine sources to the lakes that we're seeing here. And the reason we want to do that is because the modern setting guides how we interpret the paleo setting. So for this particular project, well, this is a map of Macquarie Island. It contains a lot of surface water bodies. So these lake systems are archiving rainfall, modern rainfall information and modern sea spray information together with modern ice and snowfall information, depending on where we are in the subantarctic or the Antarctic. And this is what these lakes look like in Macquarie Island. This is one of the lakes that Christina's studied, and she's got a nice core that sits adjacent to one of these lakes. And this is actually another photo of one of the lakes where Christina and her group have cored through the lakes. So there's quite a lot of water in these systems. So one of the aim of our project 2 years ago was to collect some samples from across Macquarie Island and apply these isotopic traces to understand the modern environmental conditions that are acting on these lake systems. So here is a spatial distribution map of a basic chloride concentration for Macquarie Island. So we did 40 samples from these lakes, and this is just the red dot is showing the higher chloride concentration, and as we can see, it's actually spatially quite varied. So instantly we know that there's processes occurring that are outside of a rainfall recharge signal across the island. So and we from previous studies as well as our study, we can see that this chloride concentration increase is due to marine aerosol input from the westerly wind direction. Now, what's really interesting about some of this data, this is just a plot of the major ions and how they relate to seawater. So that top curve is a seawater curve, so it's a signature. And we can see that the lake water samples, there's 40 of them, they all fit. They're all a lot more dilute than what we see in seawater. But what we see in the first, for sulfate, chloride, magnesium, and sodium, we see that there's a very similar pattern. So we know that most of these ions are being contributed from a sea spray or a marine contribution. However, when we look at some of these other elements, such as silica and calcium, we see that there's actually another distribution. So there's some other source of these ions it's not following a seawater trend. So this also fits with some of the work that Christine has done on the island, looking at paleoclimate records. And this particular graph is from a lake sediment core. Here is a radiocarbon age along the x-axis. And we have a diatom reconstruction. So it's reconstructing the salinity of that environment. And what we notice is that there is a vast difference throughout time for this reconstruction. So the salinity of this particular lake system changed dramatically over time. So this is, and this is all equated to sea spray intensity increase or decrease. Now, this is really interesting because we've got these paleo records, but we actually don't have any short-term modern information on these systems. And the lake waters themselves are showing us a lot of information, but we just don't have this long-term data set yet. So here's a map of the O18, so the oxygen 18 of the water molecule itself. And this is another distribution map. We've done this for the however many variables that we collected for, which was quite substantial. We're in the process of publishing this work. But so this is an O18 map. It can be used to show the source of the rainfall or the source of the water that has recharged those or that has interacted with those lake systems. To begin with, I've done a correlation analysis, and the O18 is not related to the size of the lake or the depth of the lake. That's really interesting because in evaporitic environments, which I study, they usually there's a relationship. So the O18 is heavier in the smaller lakes due to evaporation. So that's interesting. This O18 value is not related to rainfall because we'd see a consistent value across the island. So what we did see is that it's related to chloride concentration. So that's interesting. So my first hypothesis was that the chloride that's contributing to these lake waters is from a marine input source, and it's a droplet of some type. So as the aerosol are carried, or the droplets are carried from the wind, they're being deposited in the lake system. That was my initial interpretation. However, when we start to look at the relationship between oxygen 18 and deuterium, and this is a biplot of those two variables, we see that the waters are, there's an offset from any of the local meteoric water lines in the region. Not that there's a lot of rainfall information for these regions, which is something that's also quite lacking. There are some on the Antarctic, in Antarctica, but for this particular region, there's not a lot of rainfall records. So that's something that we want to build up also. So this offset, so if it was just rainfall and seawater droplet mixing, we would see that the samples would be plotting on a direct line to a mixing line to seawater, but we don't see that. What I'm seeing is actually a slight evaporation trend. So this is a really interesting finding because we know Macquarie Island, it's got cloud cover and it's raining constantly. So we wouldn't expect a lot of evaporation occurring. But there's something happening here, and I still need to investigate a lot more into this. That is making this the O18 more enriched compared to deuterium. So this is really interesting because we want to look at this in time series. So you can actually monitor evaporation or any of these processes if you have time series on lakes. So I'd just like to thank you all for listening. We are looking so forward to meeting you all and collaborating on this project. It's an exciting project, and we really, I've done a lot of lit review trying to find data sets for isotopic analysis in these regions, and there's just not a lot there, not compared to what we have in the inhabited continents. And we need to start to fill that data set so that we can use this information to understand the water cycle more effectively in these regions. Thank you so much.